Hi everyone, in this video I will explain how matrix multiplication is implemented in CUDA. This is one of the fundamental computational kernels which is used in so many scientific and AI applications. In the first part, I will explain how the basic algorithm is parallelized using CUDA language, and in the second part I will explain the tile algorithm. Assume we have two squared matrices M and N with the same size. In other words, the width or the number of columns and the height or the number of rows are equal. We know that the output matrix, or P, has the same size as inputs, and the value of P of I and J is the result of dot product operation on the ith row of M and the jth column of N. We also assume that the width refers to the number of columns of the input matrices. Once again, the widths of M, N, and P matrices are equal. For example, as you can see in the figure, P00 is the result of dot product operation of rows 0, or the pink row, and column 0, or the green column. To think about a parallel version of the algorithm, we may assume that each element of P is calculated by a thread. So in this example, we have to create 16 threads and formulate how threads find appropriate rows and columns. The way we formulate threads is basically done by answering a couple of questions. Let's assume that we want to instruct a thread to calculate P11. The questions are, first, how to call the thread calculating P11, and second, how to find the yellow row, and third, how to find the blue column. Let's have a quick look at the way the parallel hardware, in our case the GPU, executes the code. For simplicity, we assume there are 4 computing units. In NVIDIA, this is called streaming multiprocessor, or SM, and the input and output matrices are stored in the DRAM. Once again, in the NVIDIA term, this is called the global memory. Since we have 16 threads, with this abstract figure, the very basic idea is to assign 4 threads to each SM. For simplicity, we assume that each SM only receives 4 threads. However, in reality, each SM receives far more threads, and it can queue and switch to different threads. As you can see, in each SM, threads are numbered from 0 to 3, because each SM only sees its own thread set. There are various ways to distribute threads on SMs. For example, we can assign all 4 threads on row 0 to SM0, or we can assign all 4 threads on column 0 to SM0. But as you can see in the figure, the 4 threads assigned to SM0 are P00, P01, P10, and P11. So that means we are dividing the output matrix into 4 blocks, where each SM receives 1 block and each block contains 4 threads. This kind of 2D block representation fits the natural 2D data structure of the matrix. The assumption here is that the block width is 2, which means 2 threads in a row and 2 threads in a column. Now let's have a look at the way we index a 2D block scheme. Each block has an index for x-axis and an index for y-axis, and we write that at y, x, meaning that the leftmost index is y, or the row number, and the rightmost index is x, or the column number. Looking at the purple boundary, we see 2 blocks on y-axis and 2 blocks on x-axis. So the blocks are 0, 0 on the upper left, 0, 1 on the upper right, 1, 0 on the lower left, and 1, 1 on the lower right. Now each block has its own threads order on x and y axes, with the same philosophy that I mentioned for blocks. So each block has threads 0, 0, 0, 1, 1, 0, and 1, 1. Back to the original question. We now know that P11 is calculated by thread 11 in block 0, 0. As you can see, knowing thread 11 alone is not enough, because the same thread number exists in other blocks too. So we have to find a canonical form to find the unique row and column numbers for that thread. If we look at the matrix, we see P11 position is on row 1 and column 1 in the P matrix. that row actually refers to the row number of M, or the yellow row, and the same column refers to the column number of N, or the blue column. So if we can find the row and column numbers, we can use the same information for input matrices. The question is then, given the thread and block numbers, how we can formulate them and find the unique row and column numbers. Now let's look at how row number is formulated. We do that by looking at some elements that helps us with that. So for P00, the block number is 00 and the thread number is 00. Obviously, the row number is 0 if we know that the formula is using block and thread numbers. Moving to P10, we see that block number is still 00, but the thread number is 10. So that means we have moved one row down, which implies y index plus 1. In CUDA, we use the variable thread_idx.y for that. Moving to P20, we see that block number is 10 and thread number is 00. If you look at the figure, moving one block down on y-axis means passing the first two rows. So that resembles multiplying the block index on y-axis by the block width on y-axis. In CUDA, that is block idx.y multiplied by block dim.y. And you can verify that 1 multiplied by 2 is 2, which shows the row number. Now we can infer that for P30, we have to combine previous formulas. In other words, we have to find the block number and find the thread number in that block. So the formula is block idx.y multiplied by block dim.y plus thread idx.y. And you can verify that 1 multiplied by 2 plus 1 shows the third row. You can also use the same formula for others. For P13, we know that block idx.y is 0 and block dim.y is 2, and thread idx.y is 1, so the row number is 1. And one more example, P22 is in row number 2. Now let's see how to find the column number. Again, we go through some examples to see how we can formulate that. For P00, since the block and thread numbers are 0, the column is also 0. If we move to P01, we see that thread index on the x-axis is increased. So that means the variable thread_idx.x shows where we are in the block. If we move to P02, we see that we have passed one block and settled in the first thread in that block. So the block width on x-axis multiplied by the block index on x-axis shows which blocks we are settled on. In terms of variable, the expression is block idx.x multiplied by block dim.x. And as you can see, 1 multiplied by 2 shows column number 2. If we move to P03, similar to what I said about row calculations, we are actually combining the variables discussed so far. That means we have to find the block number and then the thread position in that block. And that is block idx.x multiplied by block dim.x plus thread idx.x, or 1 multiplied by 2 plus 1, which is column number 3. We can also check some other elements and verify that. For example, the column number for P11 is 0 multiplied by 2 plus 1, or 1. Or the column number for P23 is 1 multiplied by 2 plus 1, which is column number 3. Now let's see what we were discussing. Our goal or question was to find the row and column numbers of a thread which calculates a specific element of the output matrix. The row number we find corresponds to the row number of the first matrix, and the column number we find corresponds to the column number of the second matrix. Using that, we find the row and column number of P11 are 1 and 1 respectively. What the thread is going to do now is calculate the dot product of row number 1 of M and column number 1 of N, That means M10 multiplied by N01 plus M11 multiplied by N11 plus M12 multiplied by N21 plus M13 multiplied by N31. That means the thread is iterating over a loop doing multiply accumulation operation. Now a new problem rises, and that is how to access element of M and N. Why that's a question? Well, although we represent the matrix as a 2D structure on the paper, the same layout does not exist in memory. In fact, a 2D array is linearly stored in the memory locations. We can think about two policies, row measure and column measure, and for this example, we assume row measure representation, which will be explained in next slides. We can of course think about column measure representation after fully understand what is the process. With row measure format, the matrix elements are stored by traversing the 2D array from the first element, row 0 and column 0, to the last element, in this example, row 3 and column 3, row by row. That means when the first row is stored in the memory, the second row is stored after that, and this continues until all rows are stored in the memory. In the figure, you can see M and N are linearized in the memory space. In the first iteration, the thread has to access M10, or the yellow cell, and N01, or the blue cell. In the table, we see a bunch of variables, and the goal is to find the 1D representations in the table, which are written in the red. Looking at the linearized M, we see that to reach M10, we have to traverse one row, and that means the row number of the desired element multiplied by the width of the matrix, or in other words, 1 multiplied by width. For N01, we are in the first row and accessing column number 1. So let's write 1 for now, and you can think about accessing the head element on column number 1. In the second iteration for M11, we still have 1 multiplied by width to show that we are in the second row, and we also have to add the element position number in that row. So that is 1 multiplied by width plus 1. So as you can see, the left one is the left index of M, and the right one is the right index of M in 2D representation. For N11, we can use the same reasoning, and since the indices are same as M11, so we can find the linear index as 5. Now let's go to the third iteration. For M12, we use the same reasoning as before, because we are still in the second row. For N21, however, we have to traverse 2 rows and add the column number to that. So that is 2 multiplied by width plus 1. You may notice here that the number 2 is the same as the iteration number. We have to keep that in mind when formulating the linearized index expressions. And finally, in the fourth iteration, for M13, again we are in the second row plus a displacement of the element within that row. So that is 1 multiplied by width plus 3. For N31, we have to traverse 3 rows and add the column index to that, which is 3 multiplied by width plus 1. And here we go with the expressions where M index is a row multiplied by width plus I, and N index is I multiplied by width plus column. The final question is how to store the result in the output matrix, assuming that this matrix is also stored linearly in the memory. As you can see in the figure, to access P11, we have to traverse 1 row and add the column number to that, which is 1 multiplied by 1 plus 1, or generally said, row multiplied by width plus column. To write the kernel, we have to put all things we have discussed so far in CUDA programming language, skipping syntactical form of a kernel, which I assume you're familiar with them. First, the row and column variables are determined. And in the for loop, M and N arrays, assuming 1D row major format, are multiplied and accumulated in the variable sum. and that is later stored in the P array. And as you know, the sum variable has to be defined and initialized to 0 before the loop. All 16 threads in our example have to execute this code, and based on CUDA identifiers like block IDX, block dim, and thread IDX, access their corresponding elements in input and output matrices. You may have noticed the if block, and that is a boundary check to ensure that threads outside the boundary exit the kernel and do nothing. That is useful when matrix width and block width are not evenly divisible, and therefore the thread blocks go outside of the matrix, which means do nothing threads are created, and we want them not to execute anything as soon as we detect them. To see this algorithm in action, you can simply use the code I provided in the GitHub repository. The first step is to create input matrices. The arguments for create input file is the number of elements, and the two files contained 1D representation of matrices. The matrix mul takes two arguments, matrix width and block width. Let's try with 4 and 2. The code first prints some device specifications, and then 16 elements are read from the input files, and since the matrix width is 4, inputs are actually 4 by 4 matrices. With a block size of 2, there are 4 blocks, 2 on x and 2 on y axes. I have to say that z axis is 1 by default. In each block, there are 4 threads, again 2 on x and 2 on y. The result is 16 threads. The rest of the output shows step-by-step operations, and finally you can see the SM map where it shows each SM receives 1 block. So 4 threads on SM0, 4 on SM2, 4 on SM4, and 4 on SM6. As another example, the arguments are 4 and 4, which means there is only 1 block, and the block contains 16 threads. So there are 16 threads in total, and the SM map shows all 16 threads are mapped to one SM. And that's it. I hope the explanation is clear, and in the next part I will explain the tile algorithm. Thank you for listening.